This is bunks. Unlike humans who use GPS to travel, geese-like bunks use magnetoreception. They use the Earth's magnetic field to travel long distances in the changing seasons. Although proof of magnetoreception has continuously surfaced, scientists have wondered exactly how birds detect the geomagnetic field. There may be an answer to that question in the field of quantum biology.
It may seem crazy that a weak and barely detectable force, like the geomagnetic field, can cause chemical reactions inside a bird to tell it where to go. Well, imagine it like this.
It's hard to tip over a person standing steady, but easy if they are on one foot. So it's hard for the geomagnetic field to affect stable molecules. But if the molecules are already unstable, even the weakest force, like the Earth's magnetic field, can have an effect. Scientists found these unstable molecules in the eyes of birds, where there's a particular light-sensing protein called cryptochrome. When light hits cryptochrome, the protein releases two molecules called a radical pair. These radical molecules have lone electrons and will either recombine to form the original molecule or form a different molecule with a nearby atom. Which outcome occurs is partly dependent on the spin of the lone electrons.
Spin is a quantum characteristic of a particle. A particle can have a spin value of up or down, and a pair of particles must have opposite spins.
So before the radical molecules separate, the electrons have opposite spins. But after they split, the now lone electrons are technically not part of the same pair and can flip signs. If the sign flip happens, the molecules cannot recombine and must form a new molecule.
So wait, how does the magnetic field affect the electron's spin?
Well, spin has one more property. Remember the lone electron? It doesn't have a partner to cancel its magnetism with. This means that lone electron interacts with the protons and neutrons within the atom's nucleus, which also have spin and magnetic pull, and these interactions are called hyperfine interactions.
These interactions shake up the energy of the radical pair, because energy in the quantum world is not continuous but discrete. By not allowing the molecules into a single energy state, the particles are sent into a superposition of all allowed energy states. That is, the spin of the lone electrons are both the same spin and opposite spins simultaneously.
The electrons keep oscillating between these two states, but spend more time in one state over the other based on the direction of the magnetic field. Why? Because these molecules, like any other magnetic entity, are pulled to align themselves with the geomagnetic field, like a compass.
These graphs show the change in recombination levels when there is no magnetic field, when there is a magnetic field, and when that magnetic field is rotated by 60 degrees. Scientists theorize that the different reaction levels of recombinations will send varying signals to the bird's brain, so the bird can quite literally see the Earth's magnetic field.
And there you have it. What's even more fascinating, humans have cryptochrome molecules in their eyes too, although not the type that birds have. That said, who knows what the future of travel will look like.